So in this video, we're going to talk about change of state. We are familiar with the water cycle. In the water cycle, we have solid water, which is
Ice.
And when you add heat to ice, we get,
Water.
and then if you add more heat to water, you get vapor.
Paper.
And then what happens when we take heat away? So if we take heat away from vapor,
I know.
we get
Rain.
rain. That's right. And then from rain, if you take more heat away, you get
Snowflake.
or ice. So a change of state is basically we're altering bonds between molecules. When we're melting, we're adding energy to break the bonds so we can get a liquid. For evaporation, we're adding more energy to break the liquid bonds to get a gas. To condense and then freeze, we need to remove energy to reestablish molecular bonds.
When you add more heat, you break the molecular bonds. Take heat away, you bring the molecular bonds back. Hi, Mommy Physics class. I hope you understand the water cycle now.
So in order to change phase or state, we must overcome a certain amount of energy known as the latent heat. Latent heat can be defined as the amount of thermal energy required to change phase to phase. Since we have three phases, solid, liquid, gas, we have two different types of state changes. So we have going from solid to liquid, and then liquid to gas. So this provides us with two different types of specific latent heat definitions. First definition is a specific latent heat of fusion, which is going from solid to liquid. And that is the quantity of thermal energy required to melt 1 kilogram of a substance at its boiling point. So latent heat is also defined as the quantity of thermal energy divided by the mass. So now just to add some units to this, we know that thermal energy is, in this case, going to be measured in kilojoules and mass in kilograms. So your latent heat will be measured in kilojoules per kilogram. Okay, so now let's rearrange this equation just for fun. And I'm going to solve for my amount of thermal energy. And that's going to be mass times your specific latent heat of fusion. And this is a much prettier equation, so let's work with that. Okay, so now let's look at our second state change from liquid to gas. So we're looking at our specific latent heat of vaporization, and that is the quantity of thermal energy required to vaporize 1 kilogram of a substance. So similarly, your latent heat of vaporization, or LV, is equal to the quantity of thermal energy required over your mass. So same dimensions as before, your thermal energy is going to be in kilojoules, mass is in kilograms, and your latent heat of vaporization is going to be kilojoules per kilogram. Let's rearrange this equation again to a prettier form. So QV is equal to mass times your latent heat of vaporization. So as we're about to discover, phase changes require a large amount of energy to occur. For example, water requires 333 kilojoules per kilogram to melt ice at 0 degrees Celsius, or 2,255 kilojoules per kilogram to boil water into steam at 100 degrees Celsius. That's a lot of energy. Okay, so now let's talk about this graph. We have a substance in its solid state starting off in phase A. as time elapses, you're going to be increasing the temperature. Your first stage is going to be a substance going towards the phase change of melting. So once we've reached this temperature, we have this is going to be our specific latent heat of fusion. The word latent means hidden. So if you notice, the temperature plateaus at this stage. So where is all this hidden energy going? Well, as emerging physicists, we know that the added energy is going towards breaking up the molecular bonds required to change phases. So now we're going to continue to increase your temperature until we reach our specific latent heat of vaporization, and that's going to switch our phase from liquid to gas. As an example, gold melts at 1063 degrees Celsius. It takes 3,250 joules of energy to melt 50 grams of gold at this temperature. Determine the specific latent heat of fusion of gold. Let's write down our givens. And really important to note that you want to make sure your mass is in kilograms, so convert that to kilograms, and your thermal heat should be in kilojoules instead of joules. Okay, so now we're going to use our equation that we came up with before. So your specific latent heat of fusion is equal to your thermal heat of fusion over your mass. And we're just plugging this in, so 3.25 kilojoules over 50 times 10 to the negative 3 kilograms. And that gives us 65 kilojoules per kilogram. Therefore, the specific latent heat of fusion of gold is 65 kilojoules per kilogram. Okay, another example. The boiling point of Freon 12, an isotope of Freon, is negative 29.8 degrees Celsius. How much thermal energy is required by 455 grams of Freon 12 going from liquid phase at negative 29.8 degrees Celsius to gaseous phase at 20.2 degrees Celsius? The specific latent heat of vaporization of Freon 12 is 143 kilojoules per kilogram, and its specific heat capacity is 950 joules per kilogram times Kelvin. Let's write down our givens. Remember that we want to convert our temperatures into Kelvin, so your initial temperature is going to be add 273, so 243.2 Kelvin. Our final temperature is going to be, so same idea, add 273, 293.2 Kelvin. Our mass is in kilograms, so that's fine. Our C value, our specific heat capacity, should be in kilojoules per kilogram Kelvin, so we need to convert that. So that's just going to be 0.95 kilojoules per kilogram Kelvin. And our specific latent heat of vaporization is in the right units, kilojoules per kilogram, so that's fine. We don't need to touch that. So if we think back to our graph that we were just looking at before, we remember that we had an increase in temperature and then it hit a plateau, which was our specific latent heat of vaporization or of fusion. So we're going a little crazy with this green here. Our total energy is going to be the energy required to just get up to that temperature, plus, in this case, your temperature of vaporization. So this temperature right here. And that is going to be using our equations that we developed in the last couple days. Our thermal energy is going to be mc delta T plus, and you know your heat of vaporization is going to be mass times your specific latent heat of vaporization. So now let's sub in our values. Our total heat, or thermal energy, is going to be mass, which is 0.450 kilograms. Your C value, remember you want to use kilojoules per kilogram times Kelvin. Delta T is going to be 293.2, so your final temperature minus your initial temperature, which is 243.2 Kelvin, plus your mass again, which is, I'm just going to continue on the next line. So same mass, and your specific latent heat of vaporization is 143 kilojoules per kilogram. And that comes out to 86.68, and our units are kilojoules. So therefore, 86.68 kilojoules of thermal energy is required to change its state.